Good morning. Welcome to the first press conference of the day. This one's about first results from NASA's Orbiting Carbon Observatory. And if anyone didn't see it, there's a press kit in the back with a press release that's on the back table. Anne-Marie Elderling, who's the Deputy Project Scientist for this mission, is going to introduce the panel.
Hi, everyone. Good morning. My name's Anne-Marie Eldering, and as Peter mentioned, I'm the Deputy Project Scientist for the Orbiting Carbon Observatory 2, or Oco-2 mission, run by NASA's Jet Propulsion Laboratory. This mission is NASA's first mission dedicated to the measurement of carbon dioxide across the globe, and we're excited to be here to share some of our first results and early progress in the mission. I'm joined today by three of my colleagues. We have Chris Odell, an assistant professor at Colorado State University and one of the key members of our algorithm team. He'll talk about global maps and a little bit about the global carbon cycle. And Paul Winberg, a professor at Caltech, is our validation lead. He'll discuss the validation approach and some of the early progress. And then we're also joined by Christian Frankenberg of JPL, who pioneered, along with other scientists, our solar-induced chlorophyll fluorescent measurements. So he'll describe those and show some of the early results. So thanks again for being here with us today. So I just wanted to take a minute to remind you about some of the Oco-2 objectives in case you hadn't heard about our mission before. The focus of this mission is to gather the carbon dioxide measurements that are needed to get a first really complete picture of the geographical distribution and seasonal variations of human and natural sources of carbon dioxide and the places where that carbon dioxide is removed or absorbed or the sinks. We aim to do this on scales that we call regional or something sort of the size of the state of Colorado and over monthly periods. So this is a very demanding request. It requires a very specific kind of coverage and resolution and precision to the measurement. So we'll tell you a little bit about how we're doing that. And the other thing we want to note is that Oco-2 is an exploratory mission. Why are we Oco-2? Well, back in 2002 in NASA's Earth System Science Pathfinder program, the OCO mission was selected. That mission was built, and unfortunately, during a launch failure in 2009, the mission was lost. So Oco-2 is a rebuild of that. We got started in 2010, and we're launched just earlier this year. So we're a rebuild of that mission focused on understanding these global carbon fluxes. In the years in between that launch failure and earlier this year, we also worked closely with our colleagues from Japan on the GOSAT project, or the Greenhouse Gases Observing Satellite, to tune up our algorithms and improve our methods for getting the carbon dioxide retrievals and getting a first glimpse of CO2. So GOSAT has provided us with a glimpse of the carbon dioxide, but we actually still need the density and the precision that we'll provide from Oco-2 to answer these questions about global fluxes of carbon dioxide. So this is just a cute little movie of our launch. We launched on July 2nd out of Vandenberg Air Force Base. It was super exciting to be there and see this thing finally get into space. It took us a few weeks to get ourselves into the proper orbit and check out that the instrument and the spacecraft were working properly. We started collecting scientifically useful data about the end of September. So we're still early in things, right? We're here now in December. We've just got a couple of months of data out of what we expect to be at least a 2-year mission. So we're very early in things, but we think that the results and the promise of this mission are really quite amazing. So we wanted to share that with you today at this press conference. And now the data that we collect, I mentioned we need a very precise resolution, coverage, and precision for it. This is just a movie to show you something about the coverage. Oco-2 is in an orbit such that we come back to where we were after 16 days. So it takes us about 16 days to get global coverage of carbon dioxide. And we measure about 1 million times a day. Because of clouds and interference, we'll get tens of thousands of useful data points, which is actually a very large data set. And again, precision, you all know that carbon dioxide concentrations are about 400 parts per million these days. So out of 1 million molecules in the air, 400 are CO2. For our science, we need to understand when there's differences of 1 or 2 parts per million in these regions, from region to region. So that's a pretty demanding requirement. And we use measurements that are about 1 mile square so that the smaller footprints gives us a chance to see through some of the clouds. Okay, so enough about what we're doing. Let me show you what we've got today. So this is a map of carbon dioxide as seen by Oco-2. We've averaged data over a period of about 5 weeks from the 1st of October to November 11th. and have interpolated that and smoothed the field a little bit. But you can see already with just those 5 weeks of data, you can see a lot of features in these fields, a lot of variability. And let me tell you a little bit about what you're seeing here. So there's some features such as the banding. At the most southern latitudes, it's lighter colors, lower concentrations. Then there's higher concentrations over Africa, South America, Indonesia, and then becomes low again. And this is very typical of atmospheric gases that are emitted in different locations and then moved around by the winds. The winds of the Earth move things and mix them much more quickly along latitudes than across latitudes. And also these increased concentrations over South America and South Africa, we think some of that is due to biomass burning as well as to the biosphere. We've had some preliminary analysis with one of our postdocs to look at other data sets and help us figure this out. So he's looked at our carbon dioxide as well as the carbon monoxide, another gas that gets emitted when you burn things, especially when you burn them inefficiently. And that's measured by the MOPIT satellite. So we use that data set as well as the MODIS measurements of fire activity. And from those measurements, we see that for the southern part of Africa, there's enhanced carbon monoxide as well as carbon dioxide, showing us that fires are driving some of the enhancement that we see there. The other features that you notice is, for example, over the eastern seaboard of the US, there's somewhat of an enhancement. Again, industrialization and human activity likely to be explanation, as well as the areas over China. So these are just the first look at the data set. Again, with this 5 weeks of data, you see some interesting gradients and features. So we feel certain that once we have a larger data set with this kind of density and precision, it will really be valuable to the science community to understand the carbon dioxide fluxes. I'm going to turn things over to Chris to tell you a little bit more about what these maps are telling us and how the global carbon cycle might play into what we see here. Thank you.
Thanks, Anne-Marie. Like Anne-Marie said, I'm Chris Odell, professor at Colorado State University. I'd like to dive in a little bit more to these data sets that Anne-Marie just showed. This is similar to what Anne-Marie just showed, but it's for a shorter time period. It's just for 12 days of data. And first you see that it's spotty. These data have not been spatially interpolated, so you can see the raw data that we actually took. Also, these data were taken in what's called Glint Mode. Glint Mode is a mode that Oco-2 has, which is optimized to get data over the ocean. We spend half the time in this mode and half the time in another mode called nadir mode, where we look straight down. In nadir mode, we get very good data over land, but at the expense of getting almost no data over the ocean. So there's a trade-off there, and like I said, we spend about 50% of the time in each mode. Also in this map, you can see that we don't get data everywhere. We don't get uniform coverage. We don't get good data where it's cloudy. We need to essentially be able to see all the way to the surface. And so regions like the Amazon, you can see that we have very little data, especially in this glint mode, which, as I said, is optimized for the oceans. Also, areas that are hazy, like Eastern Asia, we don't get a lot of data all the time there either. And then finally, at the highest latitudes, we don't get a lot of data because we look at reflected sunlight off the ground. That's how we make the measurement. And if the sun is too low in the sky or not there at all, then we can't make a good measurement. But you can see we make measurements a lot of places. Now, what do we want to learn from these maps? Well, we really want to learn from Oco-2 about sources and sinks of carbon dioxide, things like fossil fuel burning, biomass burning, and the uptake and emission of carbon dioxide by plants. And one way to do this is to compare what observations we took to a model. And so this map on the bottom shows a model prediction for what we should have seen according to our best estimates of fossil fuel burning, of biomass burning, and of plant biology for these exact measurements. Now, this comes from a state-of-the-art carbon cycle model that's produced by, it's called GEOS-5, and it's produced by the Goddard Space Flight Center in Maryland. Now, if they agreed perfectly, we need OCO, right? Our models would be perfect and we would know everything. And so where they disagree are where we actually learn something. And we can disagree for two reasons. Either the underlying fluxes are slightly imperfect and we can learn from the Oco-2 observations, or the Oco-2 observations occasionally have small errors in them. And my colleague Paul will talk about how we track those errors in a second. I'm going to talk about real disagreements, which we think are driven by things we can learn about. So in this map, you see there's these regions that Anne-Marie pointed out, these red colors here, which you see are not as evident in the southern hemisphere land regions, which we think are due to biomass burning at this time of year. It's sort of the burning season in these tropical grassland regions. And in our model, it has these enhancements, but they're not as strong. You can also see these signals are actually blown out or advected over the ocean. So when you see these little hot spots, like right here in between South America and Africa, that's not an ocean flux, we believe. It's just the signature of a flux over land that's been advected out by the carbon dioxide that's just blown out over the ocean. So the ocean measurements are very important from OCO2. And finally, I just want to point out that we really see sort of the sum total or integration of flux signals from fossil fuels burning, from plant biology, et cetera. And so we need fairly sophisticated methods and tools to pick apart the different sources of signal that we're seeing in these data. And next I'm going to go to a movie which is actually the same GEOS 5 model, but now run at 3 hourly intervals. So you can see the underlying CO2 field that OCO2 is trying to measure. And you can see it's rather complicated, even though there is an average of about 400 parts per million. You can see these gradients of about 5 to 10 parts per million over the globe, and you see some interesting features. You see in this time of year, this movie is running over from October to November of just this year. You can see carbon dioxide building up in the northern hemisphere as the plants, which have been sucking carbon dioxide out of the atmosphere all summer in the northern hemisphere, start going dormant. And that allows the fossil fuel signal to become dominant, and you see the signal increasing over this time period. You also see a lot of interesting areas in other parts of the world. You see very strong plant uptake in north central Africa. You see the biomass burning and plant respiration signal, as I discussed. And finally, you see the effect of weather fronts. You can see that even though carbon dioxide might be emitted somewhere, it quickly gets sort of blown around and pushed along weather frontal boundaries and can create spatial differences of several parts per million. So it highlights that we really need the models to help inform and interpret the OCO2 observations. And with that, I'm going to turn it over to my colleague, Paul Winberg.
So as Chris mentioned, it is the differences in CO2 from place to place and over time that tell us about the sources and sinks, or the release of CO2 to the atmosphere and its uptake. And you can see these gradients really are small. They're of order a few percent at most. And therefore, there is an extreme requirement on precision and accuracy of this data in order for it to be useful. And in fact, I think measuring an atmospheric gas like this to a fraction of a percent, which is what is required, makes OCO2 really one of the most challenging remote sensing missions that has been attempted. And so when we designed OCO2 actually OCO1, back in 2001 and 2002, we realized right at the very beginning that evaluating the atmospheric data to make sure that it is accurate and precise was essential. And toward that end, we designed into the spacecraft a specific operational mode that allows us to perform evaluations in a way that has not been done before. And I'd like to show you a quick animation of that mode. It's called target mode. What you're seeing is the OCO2 Observatory as it crosses the equator and heads up the North Pacific. And in a target mode, and for example here, we're targeting a location at Caltech in Pasadena, California. And what happens is that the spacecraft essentially yaws or slews in such a way that we stare directly at one place on the ground. And there's a slight nodding that occurs, and that allows us to take an intense set of observations over a very small geographical area. And so in the next movie, what I'll show you is some data that was taken October 7th. in Southern California. And what you're seeing is the nodding of the spacecraft as we sweep across the basin. And then just when the passing is directly under the spacecraft, you'll see the smallest square, and then it increases again as the spacecraft moves to the north. So in this set of observations, this took 7 minutes, and we get 10,000 observations. And this is a real important data product that allows us to understand how the retrievals are working and how accurate they are. So if we go to the next figure. So at the center of that target is a ground-based instrument that measures the exact same quantity that Oco-2 measures. That is the total column of CO2. And when we started Oco-1 back in 2001, 2002, we initiated a network that's called the Total Carbon Column Observing Network. And this network is operated independently by a number of people around the world, but several of the stations are in fact direct children of the Oco-1 project and now used by Oco-2. This network made up the essential validation program for GOSAT as well. And I'm going to show you just 3 target modes that were obtained in very early of October. 2 of them in Southern California at Edwards Air Force Base and in Pasadena, the one I just showed you. And a 3rd one down here in Wollongong, Australia, which is just south of Sydney. So let's start on the left here. This is the 2 targets that were obtained just a few days apart in Southern California. Shown, you can see the Pasadena site and the Edwards Air Force Base. They are only 50 miles apart. And yet this is one of the largest gradients that we see in CO2 in the world at this time of year. So carbon dioxide's 3 or 4 parts per million elevated over the basin. And this is not surprising. There are a lot of cars in Los Angeles, and they're emitting a lot of carbon dioxide. And that leads to an enhancement of CO2 in the basin itself. And so this is exactly the type of data that we're intending to use to evaluate sources. Here we could estimate what the sources of CO2 are within Los Angeles. The blue up here in Edwards is very characteristic of the whole northern hemisphere at this time of year, away from these intense sources from anthropogenic activity. And on the right, here much blown up, are observations from Australia. And what I'd hope you notice here is that the CO2 concentrations broadly in the northern hemisphere are quite similar to that in the southern hemisphere at this time of year. The other thing you'll notice is that there's sort of splotchy data here in Wollongong and also in Pasadena. And that's because we've used these data to evaluate and choose only the good observations. And by good here, I mean ones which meet a number of quality measures that are required to make sure that the product we produce is accurate. And in this case, we've had to screen out the data that's obtained on the steep hills, both to the north and to the west of both sites. So that's why there's no data here. For example, the San Gabriel Mountains are very, very steep, and the retrieval does not work under those situations. So just now turn to the last figure. This shows all of the target mode observations that were made in early October. The x-axis here is the observations from the ground. These have been evaluated against the same CO2 standards that are used in the global ground-based network that is being used to map CO2 from the surface. And then on the y-axis here are the Oco-2 measurements after we have screened them and removed known biases that we have come to understand from our many years of working with the GOSAT observations. And so what I hope you'll see here is that things look indeed very, very promising. The error bars here still are rather large, but we anticipate now with the in the next few months as we continue to improve the algorithm that the precision and accuracy of these Oco-2 observations will improve substantially. And so the first look at the data quality says this is going to be a great mission, and it will very shortly be informing our understanding of the carbon cycle. And with that, I'd like to turn over to Christian Frankenberg from NASA's Jet Propulsion Lab to tell you about the fluorescence observations.
Thank you, Paul. It's my pleasure to talk today about a new data product from the OCO2, namely solar-induced chlorophyll fluorescence. First off, I have to mention that this is a data product that wasn't really envisioned in the design of the original OCO mission, but we and other NASA colleagues have recently found out that we can actually retrieve this signal from spectrometers such as GOSAT and OCO2. And the nice thing about solar-induced chlorophyll fluorescence is that it is not only just one byproduct, but it is a byproduct that helps us understand and solve the OCO2 science question, because it's tightly linked to the global carbon cycle and the atmospheric CO2 exchange with the biosphere. And I'll take you on to a journey into the inner parts of a plant leaf, where actually the action of photosynthesis is taking place. This is moving a little slow, but it's going there. So what you see is we move into the parts of a leaf, and what you will see is the chloroplast. These little things are actually the engines of basically almost all biogeochemical cycles on Earth. And in there are chlorophyll complexes, and these you can use sunlight to produce chemical energy that's basically used to build up sugars. In this process, they take up carbon dioxide and release oxygen, which enables life on Earth as we know it. But a small fraction of this light that's being absorbed is being re-emitted at longer wavelengths into fluorescence. It's about 1% of the light, and it provides us an insight into the inner workings of the plants, even if we observe it from space. So what we basically pick up from the OCO2 is the fluorescence emanating from a chlorophyll complex inside a plant leaf, and we can see it from space. And in the context of OCO2, this is really useful information because it helps us constrain the atmospheric CO2 uptake from plants, and this way we can start disentangling the various sources that constitute the net flux that Chris mentioned before. On the next slide, I'll show you an animation. So this is the first glimpse on really solar-induced fluorescence data from the OCO2 mission. This is an animation over 3 months from OCO2 from August through October. It's worth mentioning that this time period is the transition from the growing to the dormant season in the northern hemisphere. So if you focus your eyes on, for instance, the US, in August, you should go back there. In August, you still see it active. This is the US Corn Belt, highly active still in August, but then you see the dormant season kicking in from September to October, where basically the entire northern hemisphere is shutting down photosynthesis. And that's the time period when the plants start releasing CO2 in the respiration process. If you also look at the African belt here, what we saw in Chris's slides before was the strong uptake in the African belt, and this is nicely shown here in the fluorescence data, where we see strong photosynthetic activities in the northern part of Africa, and we have this typical seesaw pattern where in this time period, this area is highly active, and the biomass burning season is basically taking place at the other pole of Africa, and this switches in season. So these are nice features that we can look at with the OCO2 data. On the next slide, we really used all of the available OCO2 data that we have so far from August through October 2014. There are millions and millions of spectra that went into this image, where I display it on a much finer color scale so that you can see finer details of the solar-induced chlorophyll fluorescence data from the OCO2 satellite. And we can really see rich details in this data set, which is, especially in the tropical Amazon, we already see kind of start to disentangle different areas. You see this area here, which is in this time period completely dormant, which is not that accurately seen by other satellites or other methods. And we see sharp gradients here, for instance, where you see mountain boundaries or desert boundaries in other areas of the Earth, or these little belts here across Australia. So to summarize, this is really a new data product from the OCO2 mission, basically a bonus data product because it wasn't envisioned before. But our hope is that in the future, together with the atmospheric CO2 measurements, we can help better constrain the processes of the carbon cycle as opposed to just measure net fluxes and then trying to find out how these fluxes were constituted. And with that, I'll hand off back to Anne-Marie, who will conclude.
Great. Thanks, Christian. Thank you, everyone, for joining us in our press conference. So just to remind you of the key points here, we're excited to show you the early data from OCO2. We believe the data coverage, precision, and resolution that we have is really going to be beneficial to answer our key science questions about the sources and sinks. We're working very hard to carefully validate this data set against internationally accepted measurements of carbon dioxide, as Paul described. And as Christian just told you about, the new solar-induced fluorescence will be a very powerful product in looking at the CO2 and understanding a little more about natural carbon cycle. I also wanted to mention that as you know, NASA has an open data policy, so we're doing our work to rapidly get this data out and share with others. At the end of December, we'll be releasing the first stage of our data, the radiance or light level measurements, and then later in March, we'll have the carbon dioxide available for everybody. So these are a couple of links about where you can find more on our mission and where the data will be posted. We're happy to answer questions, and thanks again for joining us.
Hi, yeah, Eric Hand with Science Magazine. I guess I have a couple questions for Anne-Marie. I don't know if you can go back to your original map,
Sure.
the main image that you...
Here we go.
Yeah, terrific. So I guess my first question is if you could tell us, how this map would best be made before, how this represents improvements over existing models and observations. What would be the best way to make this map before OCO2? And then also, you kind of talked about some things you're seeing in this snapshot in this particular moment, but maybe you can say something about overall goals for the mission and how you can, with time, maybe you can explain some of the questions you have about the net fluxes.
Okay, I'll do my best, Eric. So as I mentioned, this map includes about 600,000 data points over this 5-week period. If we were trying to make an image similar to this before the OCO2 data was available, we'd have a much smaller data set to work with. In a time period like this, the GOSAT measurements would probably be in the order of 1 or 2% of that volume of data. We have designed this mission so that we collect glint data over a very wide latitude range, and in previous measurements, those latitude range were a bit more restricted. So you typically would not have had all of the ocean measurements over this period from previous data sets. And I think we can extract a little bit more information about these regional scales because of the density of the data that we've collected here. And in terms of learning about the fluxes, I think as Chris tried to explain that you're not able to just look at the features in this map and say this is where the carbon dioxide came from, because we have both sources, sinks, and mixing in the atmosphere all playing a role in the final field that you see with these measurements. So we'll be using this data with the atmospheric models to kind of, as Christian likes to point out, you sort of run the model in reverse and say, I saw CO2 here, where did it come from? So we'll run those models in reverse and try to find out where the source must have been if we observed it where we did. After we have a few months of data and good carbon dioxide estimates, the global modeling community will really take up this data and use their techniques to try to back out those fluxes.
Harvey Lyford, freelance. I'm not really too clear on the TCON. Exactly what instruments are there at these stations? And on the map, it seemed to me that in Europe and North America, they were mostly land-based, and in the rest of the world, they were in the ocean, presumably on islands. Why is that?
We'll let Paul explain.
The instrumentation used for the ground-based network is a solar viewing spectrometer. So essentially, we take spectra, much like OCO2 does, but we take them directly of the sun. And as a result, we are able to make a very precise measurement of the CO2 abundance. And these data then are characterized very carefully by taking profile observations from aircraft. So in that way, we're able to essentially calibrate the ground-based network such that it is entirely consistent with the data that are being obtained globally in the surface networks. Those are operated by NOAA, for example, or from Scripps and their international partners. So TCON actually essentially is the transfer standard between the ground-based network and the spacecraft observations. You asked about the coverage in the tropics. So again, these observations, the ground-based measurements are made in partnership with different organizations around the world. OCO-2 put together and helps to operate the only one tropical station. That's the one in Darwin, Australia. And the others are run by organizations, mostly European organizations. And so the locations are really much more about the infrastructure and the availability of organizations who want to set up an operation there. Does that answer your question? Yeah.
Rick Lovett, freelance. So as I understand this is looking at the reflected spectrum of the sun, and so slopes don't work because of what, and what is glint mode?
Sure. So we actually make our measurement by ratioing. We measure the total, literally the total number of carbon dioxide molecules along the path that the sunlight traveled. And that just gives you an absolute number. It's like so many moles per square meter of the atmosphere. And to get a carbon dioxide concentration, like 394 parts per million, you need to know how much dry air was along that same path. And we do that by actually measuring the oxygen concentration as well as measuring carbon dioxide. So OCO2 actually also measures two gases, carbon dioxide and oxygen. But oxygen we use as a reference because we believe we know its concentration very, very accurately. And so by ratioing the amount of carbon dioxide along the path to the amount of oxygen along the path, we can get out the carbon dioxide concentration. Now, why doesn't it work along slopes as well? That's because it's tricky. We have to know the surface elevation very accurately, and so if the surface elevation is changing very rapidly in our field of view, it introduces much more sizable errors. And so for the moment, we screen those out as because we have sufficient observations where that's not the case. You asked about glint mode. So glint mode is the oceans are very, very dark. We don't always get this sense when we think of the oceans as blue, but really they're black. They absorb most sunlight that's incident upon them, and they reflect it, along a specular direction like a mirror, right? And so we really, if we're looking from space, if the sun's coming in and we're looking from the satellite, we can only see if we're looking towards that sort of mirror image or specular, what's called the specular direction. And so we have to point fairly accurately to see that signal. Whereas over land, that's not the case. You don't need to do that. And so this is how we can get signals over the ocean, and so we call this glint mode, to see that ocean glint signal.
Anne-Marie, you mentioned that this is mostly research on carbon, the carbon flux. But is there a role to be played in sort of the discussions around verifications because of new climate treaties that this could fit into the other kinds of data being collected from surface observations such as what NOAA would make?
Right. So we often talk about our measurements as just another tool in the toolbox. We're very much focused on the natural carbon cycle. The design of the global sampling is really well suited for the natural carbon cycle, less well suited for anthropogenic emissions because we often miss big cities and we're not targeted focusing on those. We imagine what will happen is as we improve these natural fluxes, it'll help those who are trying to learn more about what's happening from the anthropogenic burning. So we probably don't have a direct contribution, but I think in the larger discussion and our understanding of how carbon flows are happening, that will reduce some uncertainty in these areas that may be useful as people try to understand what our contribution is. So I would say there's no direct application to a verification application, but there's a big contribution to the carbon cycle uncertainty reduction from our work.
Jonathan Amos, BBC, kind of related to that as well. Do the lessons learned with the TCON exercise allow you to go and target cities that don't have that ground instrumentation? I mean, can you go and target Beijing? Can you go and target Rotterdam? I don't know, any of these cities that are associated with large emissions and say something interesting about them because of what you've done with the TCON?
Yes, I think the answer is certainly, and there are discussions going on now as to whether we can increase the number of places that we can target to look at other interesting locations, such as those you mentioned. More importantly, though, we're all hoping that there's a follow-on mission called OCO-3 which would directly provide that flexibility in operations.
Gabriel Popkin, freelance. Two questions. One, you're looking, as I understand it, you're looking at the total column of CO2. So does that mean that you're not getting any vertical data within that column? And are there major gradients within that column, or is that not a concern? And then my second question is, on that map you showed where the hotspots seem to be over the major tropical forests, I mean, can we infer that those forests are all carbon sources, or is that kind of too simplistic a view of that? Thanks.
Yeah. So to answer the first question, we essentially do just see the total column. There is some ability in the spectra of sunlight we see to attempt to get more information about how the carbon dioxide varies in the vertical. But for the most part, we are a total column mission, and the way the measurements work is, at this point, I would say it's an exploratory activity at this point to try to get vertical information. As for a limitation, it is a minor limitation, but our sensitivity peaks closer to the surface, so we actually get a little more information about carbon dioxide closer to the surface than we do higher up in the atmosphere, and that gives us more direct information about the sources and sinks that are coming from the surface. And can you repeat the second question? Oh, right. Are they net sources? They are right now. Okay, they are at this time of year, but they will turn to net sinks 6 months later or 4 months later. And so to see if they're a sink overall, you have to have at least a year of data. So most areas on Earth are strong net sources where if there's a lot of plants during part of the year, and strong net sinks the other part of the year. And to see if they're overall a net sink or a net source, you have to have at least a year of data.
Yes, this is a question from the chat. It's a question from Jillian Kemsley at Chemical and Engineering News. Is there anything about how OCO2 is working so far that has surprised the team?
Is there anything that surprised the team? Of course, there's always surprises when you first get these things in space. I think overall we're very, very satisfied with the performance of the instrument. There was a little bit of a surprise early in the mission when we realized our sensitivity to the polarized light wasn't as we had planned. And so there were small bands of latitudes at higher northern latitudes where this reduced the signal. We developed a strategy where we just changed our way we use the spacecraft and rotated a little bit and picked back up the light that we wanted to sense. And so now we have measurements with sensitivity similar across the whole globe, more than adequate signal across the whole globe. So I think we've overcome that surprise. At this point, it's what we call technical fun. As we look into the data set, there's always a few features that you maybe didn't realize you were going to have, and then you have to work your way around them. But overall, I think we're meeting all of the expectations that we had for the spacecraft and the instrument's performance, and it's turning out wonderful for the science.
Hi, Rich Monastersky from Nature. Just a couple of questions. If you can just specify, comparing these data to GOSAT, what is the change in resolution or difference in resolution and the volume of the data, the precision? So that's one question. And then when you look at the data and you're throwing out sort of the data that don't meet the quality, what percentage are being thrown out, and is that higher or lower than what you would have expected?
Let me get the high level, and then you can talk about the screening a little bit.
Sure. So in terms of how are these different than GOSAT, GOSAT it had fairly precise measurements, but only had about one observation every 200 kilometers. And its spot sizes on the ground were much, much larger. They were about 10 kilometers across, or 50 square kilometer circles, roughly. In terms of precision, our signal-to-noise ratio is somewhat higher than GOSAT, so we do expect that once we fully understand all our systematic errors, that our individual shot errors, if you will be a little bit lower as well. But mainly, we take about 100 times as much data than the GOSAT instrument took, and I think this is one of the primary differences.
And then, what was the last part of your question, Rich? Was the Oh, the screening, yeah. So, I mean, at this point, we're, I think, early in the game in terms of the screening of the data. We have some things we learned with GOSAT about where your problems typically come from, so we're kind of focusing on those features. We will develop a more sophisticated approach to the data screening once we've got a full data set to look at. So our plan is actually to try to use some of the features in the spectra themselves to know which ones will be good and which ones won't, and then we'll only process what we think will be good data. So we have sort of a goal of processing about 6% of the data, and our hope is that 3/4 of that will turn out to be really useful once it's through our processing system. So that's where we get these numbers of sort of tens of thousands of useful data coming out of the million measurements a day.
The one thing that I think is important to realize is that the measurement only works for CO2, that is, when there are no clouds. And so most of the screening that has to happen is just that. It's to remove scenes where there's even a whiff of cloud. And this is one of the big advantages of OCO2 relative to GOSAT, which is with that small footprint, 50 times smaller footprint. If you think about it, you're on an airplane and you're looking down and you're trying to see through the clouds. It's much easier when you're trying to look at a 1 kilometer by 1 kilometer patch than if you're trying to find a 50 square kilometer clear spot.
This is Dan Vergano with National Geographic. I had 2 questions about the chlorophyll fluorescence. The first is, it seems like you're taking measurements on land. Why is that? And if I'm wrong, tell me. And the second thing I'm wondering is this going to give you a product that you can eventually subtract away from the other measurements of OCO2 and see what's anthropogenic and what isn't? Or how far can you take it?
Okay, let me start. I just gridded it only over land. We also take measurements over the ocean, but the signal is an order of magnitude lower over the oceans, even though there's also chlorophyll fluorescence from phytoplankton in the oceans, but it's a magnitude lower than what we see over land, to answer your first question. Maybe the other one, I would also like to mention that, maybe we can go to the next slide, which is a little. What you see here on this one is also a much higher density than we do for OCO2, for the atmospheric CO2 measurements, which is caused by the fact that the fluorescence measurements are actually not that sensitive to cloud. So for the fluorescence retrievals, we can use a much higher percentage of data and get a much finer picture on Earth. And eventually, yes, we will. It's not as easy as subtracting the data from the fluxes, but we can put the measurements of solar-induced fluorescence into the models that we actually use to retrieve, to invert the net carbon exchange, and this will help us to constrain one part of the flux equations, which is, in principle, the net ecosystem exchange of the biosphere is the sum of the photosynthetic uptake and the respiratory release. So this will give us a constraint on one part of it. And if we know this and put it in the model, we should be able to disentangle these 2 main components of the carbon cycle. That's the long-term goal. Yeah.
Rick Lovett, freelance again. I'm still a little confused about the technology here. The quick question, I hope, or a quick answer is what I'm looking for. When it's looking down on land, it's getting a reflection off something. What keeps the something from mucking up the spectrum you're looking at so you can't tell what you've got?
That's a great question. The short answer is that let's say that the something underneath is just soil, okay, and the light is reflecting off dirt on the ground. Because it's a bulk property, it actually doesn't have strong spectral features like the gas absorption that happens in the atmosphere. So we're really looking at these very fine sort of features in the spectrum that are signatures of the absorption of light by carbon dioxide or oxygen, and that simply is not the case on the ground, where there are variations with color of how the ground reflects sunlight, but they're much, much smoother. So they really don't muck up the signal.
I have a question from the chat, again from Irene Klotz from Discovery Channel News and Reuters. Once scientists understand better how to use the OCO2 dataset, will specific CO2 emitters like a power plant or a factory in Beijing be able to be identified? And if so, when will that sort of info be available?
So again, our OCO2 focus is really on the regional scale monthly sort of timeline of the carbon dioxide sources and sinks. And we think from this data that will be achieved with this mission. If you're thinking about individual sources, we'll not really have the right view for that. But as Paul mentioned, we're trying to get a mission up onto the International Space Station that has a more focused mapping capability. And if that were to happen, that might provide some real opportunity. We're struggling with that mission because we don't have funding right now. If it were funded, it would be something on the order of the 2018 kind of time frame where that sort of data might become available.
Thank you.
We have time for one or two more questions. Do we have any here from the floor?
Hi, Howard Lee, freelance. A couple, if I may. Just coming up to what you just said with the long lead times for getting missions launched, and you mentioned a 2-year lifetime. Presumably OCO3 is kind of being built right now. And the other question, if I can sneak that in, is you mentioned that you're backing out carbon dioxide by reference to oxygen. It sounds like you're assuming oxygen is constant, and I'm not sure that it is, so can you talk us through that one?
So I'll tell you a little bit about OCO3, and then one of these guys will tell you about oxygen. So I think there's two key points. One is 2-year nominal lifetime. The broad experience has been that most of these missions last past their nominal lifetime. We certainly hope that's the case with OCO2. It was built as an exploratory mission, so we probably won't get 20 years, but maybe we'll get 5 or something. So we'll to see where that goes. And then with OCO3, OCO3 is built around a spare copy of OCO2. So there was actually an instrument build that's a backup. It exists. It's sitting around. I can show you slides of it tomorrow. So the hardware is all pretty much there. We're doing some adaptation for ISS, so that's the part of the thing that needs to get built. But the heart of the spectrometer exists, and it's in storage. It's sitting around today. Who wants to talk about oxygen, Paul?
Well, I can. Yeah, so oxygen, the constancy of oxygen. If we're talking about dry air, then the mole mixing ratio, or the fraction of the dry air that is oxygen, is incredibly constant across the Earth. Geochemists are actually measuring this quantity because the minute changes that you do see, mostly due to the fixing of carbon dioxide and the release of oxygen, cause a teeny signal, much, much smaller than the kinds of signals that we're seeing here with carbon dioxide. So we're very comfortable with that assumption. It's something that is actually being measured, and the changes are very, very small.
Okay, we're out of time now. So thank you, speakers, for your presentations, and thanks everyone for being here and asking questions. Our next press conference will be at 10:30 a.m. Actually, it's not a press conference, it's a workshop for writers. It's on refilling California's reservoirs, the storm aerosol connection.